Hi, my name is Sudarshan. Welcome to my channel EasyML. In this video, we will delve into the second branch of unsupervised learning, that is dimension reduction. As I explained in the introductory video, we will be exploring how we can deploy principal component analysis or PCA for dimension reduction. For those of you who need a refresher, please click on the link provided below. Let us now explore the concepts that are a prerequisite to principal component analysis. So, what is principal component analysis or PCA? We know that PCA is a dimension reduction technique. But before understanding PCA, let us first try and understand what we mean by dimension reduction. Here, on the left, I have a statue of the Eiffel Tower. This statue is a three-dimensional object. Now, let us say I invite an artist and ask him to draw a sketch of this statue. On the right, I have that sketch of the Eiffel Tower. This sketch or drawing is now a two-dimensional object. So, if I point at the statue on the left or the drawing on the right and ask somebody what the object in question is, they will be able to very easily identify it as the Eiffel Tower, correct? So in this case, whether the object is three-dimensional or two-dimensional has no bearing on the person's ability to identify this object as the Eiffel Tower, right? So this is called dimension reduction. The process where I reduce the dimensions in the data whilst still capturing the underlying essence of the data. So, in a given data set, if I have variables that are heavily interrelated, then they can be combined or grouped together. This brings us to the definition of PCA. Principal component analysis or PCA is a procedure where we transform linearly correlated variables into a set of new variables that are called principal components. And these principal components are linearly uncorrelated. Here, when I mean linearly correlated, it essentially means that the variables are interrelated. Now, let us see how we can spot whether or not variables are linearly correlated or interrelated, in other words. It is important for you to note that only if the variables are interrelated or linearly correlated are they eligible for PCA. So the way to understand whether variables are interrelated or not is by looking at the correlation, as some of you might have already guessed by now. So here on the left, I have a correlation matrix. Here, you can observe that the variables height, weight, and age are highly correlated amongst one another. The average correlation amongst these variables is roughly 0.7. And if you can recall, when I explained the correlation matrix and the correlation spectrum, I had also explained that if the correlation coefficient was somewhere between 0.5 to 0.9, then the correlation between the variables is deemed to be strong. For those of you who need a refresher on correlation, please click on the link provided below. So here we can say in this case that these variables have a strong correlation amongst one another because the average correlation is 0.71. Now, it is also important for you to note that if the average correlation amongst the variables in a given data set is greater than 0.3 or less than minus 0.3, then those correlations are deemed to be significant, or we can say that the variables are linearly dependent and therefore eligible for PCA. Let us now explore a sample use case. Why would someone want to perform principal component analysis? Well, here I have the variables height, weight, and age. As I explained in the introductory video, if the analyst wanted to derive a new variable that is kind of similar to BMI, he or she can perform PCA on these set of variables. PCA will mathematically combine the essence of these three variables into one new variable. In the next video, we will see what we mean by mathematically combining variables. We will explore how PCA models are built. So thank you and stay tuned.